Welcome to the course 1131 on today, April the 1st. So it's not a joke, we're having a real course. So today's course will be on the best way to build concurrent programs, which is deterministic data flow with ports. So let me start by showing some slides. So we're going to show how to build concurrent programs in a way that makes them as easy as possible. So we know building concurrent programs is hard. In multi-agent programming, which we saw last week, we built the lift control system, you built the state diagrams, you have to make sure that all the messages can happen at any time. So this is difficult, okay? It's difficult to do this in general when you have a lot of agents. But on the other hand, we saw before another model, deterministic data flow, which is actually much easier. It's actually so easy that you can add threads wherever you want. So the question is, can we somehow get the advantages of deterministic data flow and still do general distributed programming? So deterministic data flow has limitations, but can we keep those advantages of it and do general concurrent programs? This is possible. It's what we're going to see today. So this gives us the best way to write concurrent programs, the best way that I know of, the best way to make them easy to write, easy to understand, easy to prove correct, is you start with deterministic data flow and you use it as much as possible, but you cannot use it everywhere. Sometimes you need to do other things. Sometimes you need ports. Remember the client server? We had the client server application here, 2 clients and a server. There can be millions of clients. So this program, most of it can be written in deterministic data flow. There's only one port is needed here. Right there, where the server receives the message. This whole program, it might have millions of lines of code. It only needs one port. So this is the approach. So usually you only need a very small number of ports. So today I'm going to show you how to do this with some practical examples. I'm going to give some designs that use this approach, and then you'll see how it works. So the first example I want to give is called concurrent composition. This is an introductory example to get your neurons warmed up this morning. So let's recall the thread statement. So when you do thread end, you create a thread, and this thread executes independently, okay? This other thread executes independently. So with these 2 instructions, we have created 2 independent threads with 2 instructions, and the original thread continues. So we have 3 threads, they're all independent. But sometimes this is not good enough. Sometimes you have to wait. Sometimes the original thread creates 2 threads, and it has to wait until the 2 threads are done. Maybe it does subtasks. It does some worker task, and it has to wait until the task is done. So this gives us a new operation called concurrent composition. So I introduced this notation for it here with the 2 vertical bar. This is a notation that people usually use. This creates 2 threads, and it waits until both are terminated. So the instruction S3 will only execute when S1 and S2 threads are done. So this operation is called concurrent composition. It's in opposition to sequential composition. Here we have created 2 concurrent entities, 2 threads, and we wait until they're done before continuing. So let's see how to program this. So we can actually implement this using the single assignment data flow variables. So here's a piece of code that implements this. So we introduce these two variables, x1 and x2, we'll use those to wait, to synchronize. And so we create the two threads. So we execute S1 in the first thread, but when S1 is done, we'll do x1 equal unit. And when S2 is done, we'll do x2 equal unit. And in the original thread, we wait until x1 and x2 are bound. So the wait operation will wait until bound, until x1 and x2 are bound. We use this special constant unit. It could be any constant, but the constant unit, we use it to say that we don't really care about the value. We just want to know that there's a constant. So there's a constant that allows us to say that, which is called unit. So these two wait statements will wait until both threads are done, and the original thread will continue when both subordinate threads are done. So this is how to implement concurrent composition. Okay, let me go just for a second back to the chat to see whether everything is fine. So everything is going fine now. Remember that if you don't hear me, if there's a problem, please unmute and tell me so I can fix it. So I'm assuming everything is going okay. So let me show now how to implement this. We're going to write some code. Let me go back to the slides and show how to build an abstraction to implement this. So we go back now to the slides. So this is his example, is verbose. We don't want to write this kind of code all the time. So we're going to build an abstraction now to do concurrent composition. So we're going to use higher order programming to implement a general form of concurrent composition where we have n instructions from S1 to Sn. And we can write these instructions in the language using higher order as procedures. So the instruction S1 will be an anonymous zero argument procedure here. So this is something we can give as an argument then. We will define a procedure. I will call it barrier because concurrent composition is sometimes called barrier synchronization. The idea is that if we have a whole bunch of threads, so these are all the threads, then we wait, the original thread waits until all the other threads are done. So there's a kind of barrier, a wall. It waits until all the subordinate threads are done, and then it continues. So it's also sometimes called barrier synchronization. So let me call it barrier. And the argument to barrier is PS, which is a list of statements. So a list of zero argument procedures. So barrier is actually very easy to write using higher order abstractions. Here, the PS argument here is given. We first do a map, and then we do a for all. So the map here will take each of these procedures and apply this function. So you see the P argument is going to be a procedure. So we will create a thread here, thread end. In this thread, we will execute P. We also have a local variable X, and we will do X equal unit inside the thread after P is done. And then finally, we will return X. So the result of the map is the map will create threads for all the procedures, and it will set up all the variables, and it will return a list of all these variables. So you see the map is doing a lot of good work here. And then we will have this for statement. This is basically a for all. This will execute the body for all the elements of XS. So for each variable X in XS, so here I'm introducing X. So here it's like a local statement. I'm introducing X, I'm defining it, and the for will create weights, will do weights for every X in XS. So here we're doing all the weights. So we create the threads, we create the data flow variables, and then we wait. So notice this barrier can be written 100% completely using deterministic data flow. So let me create this now. But first, let me show you an example, and then we'll write some code. Here's a piece of code running barrier, but it's nested. So here we have the top call of barrier, which has two procedures. The nested call, which also has two procedures. Notice they have delays. So the top call of barrier will do two things. The first procedure will wait for 500 milliseconds, delay 500, and then it will create two new threads. The first one waits for 200, the second one waits for 400. And the first one will then browse C, the second one will browse D. And when both of these are done, the barrier, then we will browse E. All of this is going on concurrently with another procedure that will wait for 600 milliseconds and then browse E. So the question now is, what is this program going to display? Okay. Now, to figure that out, remember exactly what delay means. So I've told you delay n means to delay the current thread for n milliseconds, but it's very precisely, it's for at least n milliseconds, not less. It could be n or more, because it cannot be exactly n, because the scheduler cannot guarantee after the thread is runnable when it will actually choose that thread. There might be other things going on, okay? So all we can say is that it's at least. But most of the time it will be very close to it, but not guaranteed. So assuming that the delay will be very close to that time, so delay 500 waits very close to 500 milliseconds, what will this program display? So you have to figure out all the delays. So what's the first thing that it's displayed? Well, after 600 milliseconds, it will display E. After 500 plus 200, it will display C. So that's 700. And after 500 plus 400, which is 900, it'll display D. So it should display E first, and then C, and then D, and then this one must come after the other because of the barrier, so it will display another E. So this is, most of the time, it will display E, C, D, E. Okay, let me now write some code for you. I want to make this thing work in real life. So let me go back. First of all, to see, do you have any questions on this? Is this understandable so far? So now I'm going to write some code. Okay. So now I'm going to go to the screen here, and I'm going to write the barrier synchronization, and I'm going to show you how it works. Oops. So it's a procedure barrier that has a list of procedures as argument. First we do a map. So the map will take all the procedures, the zero argument procedures, and it will create a thread. Let me do it piece by piece. It will create a thread with each procedure. Then it will mark the end by binding to unit. And here we have to declare X, like this. And finally, the function returns X. Okay, so this is the map. And now we will do a for loop. We will take all the X's in XS and do a wait for each of them. So this is barrier synchronization. Okay, you see it's very simple with higher order, Nissa. You see that programming languages that support higher order, there are many of them, functional languages typically, and even today now Java also will support it in Java 8. That makes it very compact. Higher order lets you build abstractions in a very compact way. So I compile barrier now, and now let's see an example of barrier synchronization. So let me try now barrier with some procedures. Let me try barrier with 3 statements. So let me do here a first one. Delay 100, browse A. In the second one, let me now be a little bit smarter here, a little bit more tricky. Let me create a nested call to barrier. Like this, with 2 barriers. Okay. And now let me do a browse of B. Let me do now a third one. Browse of C. Let me now do a little bit farther. Let me nest again. So I'm going to try to make you think a little bit so early in the morning. Delay 50. Browse D. Delay 150. Browse E. Let me make it a little bit wider, like this. And now let me put a browse F. Let me put here, before this barrier, let me put in a little delay here. 25 milliseconds. So here we have now an interesting piece of code that will create lots of threads. And at the very end here, I will put a browse of G. So when I run this, what is it going to display? So I'm going to assume that the delay will be almost the right value, that will not wait much longer. So after 100 milliseconds, it will display A. After how much? After 200 milliseconds, it will display C. Okay. At the very end, it will display G. I know that the G has to come when everything else is done because of the barrier synchronization. And then here, what's going to happen here? Let me do a browse H here. So if I look now at this internal barrier, this browse H will be after 25 milliseconds. Okay. And what about these guys? So the F will also be after 25. So they're both 25. Which one will be first? Well, that depends on the scheduler rules. I have now the completely internal one. So D will be after 75 milliseconds. Okay. And E will be after 175 milliseconds. So this is the order in which these guys are going to be done. The B will be after F and H for sure, because of the barrier synchronization here. The B has to come after this barrier. So the first two should be H and F. Which one will be actually printed first? Well, it depends on the scheduler. Depends on how the threads are created. Typically, the first thread that's being created. So this this thread is created at a certain time. This thread will, so these two threads, this thread will be created first before this thread. So that means the scheduler will give it a time slice immediately. So probably the F will be first, if I'm reasoning right. Unless the scheduler has other things going on. There's no guarantee of all this. So I execute this now. So you see what's happening here? H. Okay, I made a mistake with F. You see, I made a mistake. The F will guarantee be after D and E because of the barrier synchronization. See, it's not so simple. So the F is guaranteed after D and E. So H is displayed first, and then D, 75 milliseconds, and then A, 100, and then E, 175, and then F. F comes after D and E, that's correct. And then B comes after F and H, that's correct. Okay, and then C, 200 milliseconds, and then G at the very end. You see, this is correct, huh? So you see that you have to be a little bit careful when you figure out when things are executed. You also see that you can use delay to force certain order or something. Use delay to, it's not really force, gently advise the scheduler for an order. There is no way, it's very hard to force the scheduler actually. Because the scheduler, there might be other things going on in the system, and once the thread is runnable, it might not run immediately. It could run a little bit later. Okay, so you see how that works? Is that okay? Anybody questions on that? Okay, there are some questions. One question, I have not clearly understood what the barrier exactly does. Well, what happens is the barrier has input statements, 1, 2, 3, up to n. It will create n threads, and all the threads start running, and then the barrier will wait until all those n threads are done. So the original thread, the one that created the n threads, will wait until they're all done. So it's like creating a barrier, a wall. The original thread will only go on when all the others are done. Okay? So this program, so the barrier itself, so there's another question, is this non-deterministic? The barrier is deterministic. It's not non-deterministic because the behavior is completely always the same. The barrier will continue the original thread when all the others are done. It's always the same. There's no variation. What will vary is the speeds of the threads, of course. The barrier is guaranteeing synchronization when all the threads are done, but that's all it does. Internally, those n threads will be running at different speeds between themselves, and the scheduler will be free to choose them in any order. According to the rules, okay, so they will be given time slices. When you create a thread, you start by giving the time slice, a piece of the processor for 10 milliseconds, and then when the time slice is done, it goes to the next thread. Unless the thread stops earlier, and then the scheduler immediately picks another thread. So you see the scheduler has a lot of freedom to choose which thread executes. So you can see how we have an interesting program. The barrier itself is deterministic, but it's creating threads which will maybe be non-deterministic. Okay? So it's a little bit subtle, but it's important to understand how it works. So let me show you a slide. Here. Okay. So we have created this higher order abstraction, okay? So the barrier will actually wait until all these instructions are done. They all execute in their own threads, and the threads, once the threads are created, they're independent, and the speeds can change, but the only thing you synchronize on is that the threads are done. So that's deterministic, but the threads internally will still be non-deterministic, okay? So you can see here, the order in which it's displayed is most of the time going to be deterministic. And this is because the delay itself does not actually guarantee an exact time. It only gives you a minimum, a lower bound on when the thread will execute. Okay? So this is our first example. This is barrier synchronization, which is also called concurrent composition. And notice this is completely written in deterministic data flow. Okay? So this example, we don't need ports to write barrier. It's completely deterministic data flow. Of course, inside these threads, you can do anything you want. Maybe non-deterministic things. But the barrier abstraction is deterministic. Okay? So let me go on now and go a little bit farther than this. Okay, there's another point. Some programming languages allow defining new syntax. Some languages let you define new syntaxes. Some typical of the functional languages let you do that. So we could actually define a new instruction called conc-end, concurrent composition. And we define a translation of this into a call to barrier. You see where each one of these instructions turns into a zero argument procedure. So this could be invisible to the programmer. So the programmer then has a new abstraction that he or she can use for writing programs. Okay? So, and this is a deterministic abstraction. It introduces no non-determinism because it is written using deterministic data flow. Okay? So this is not possible in Oz. In Oz, you cannot define new syntax like this. But there are languages that let you do that. Will let you define new syntax. A language like Scheme, for example, has something called macros, where it could define such a new syntax. Okay? Well, let me go on now and go a little bit farther than barrier. Okay? We'll now look at when the number of threads can be variable. So the concurrent composition, the barrier, we have S1 to Sn. Notice the n, we know the n statically. It's the length of the list argument to barrier. It's known in advance. Okay? In the concurrent composition, we know when it starts how many threads we will create. We will create n threads here. Okay? So let's go farther now. Assume now the number of threads is not known, that during the execution we can create more threads. Assume we have a computation that can create new threads dynamically. That means we can create a thread, and inside that thread we can create another thread, and maybe more recursively. So the number of threads, we do not know them in advance. And we want to synchronize on the termination of all these created threads. You see what we're doing here. It's much more dynamic than concurrent composition. We build a thread, we create threads, maybe we create a few threads, and each one of them is running a program. Maybe it creates more threads, and those will create even more threads, and more and more and more. And we want to synchronize on all of those threads terminating, and we do not know how many there are in advance. You see, we're actually very ambitious here. This does not seem very easy to do. Okay? So new threads can themselves create new threads. So you see, this goes much beyond the regular concurrent composition. New threads can create new threads. It's like the thread statement. You know, when I do thread end, the S can also create threads, of course. But now we want to synchronize on all of these threads terminating, and we have no idea how many there are in advance, and there could be hundreds, thousands, who knows? Depends on the execution. It could even be non-deterministic, how many threads are created. Okay, this new abstraction, the new one, we want to build now an abstraction to do this. Okay, dynamic concurrent composition. We cannot write this one in deterministic data flow because this one actually is non-deterministic. The number of threads might depend on the scheduler choice. There might be and the order in which the threads are created is not known. In order to write this abstraction, we will actually need a port. We can write this using one port. So now I'm sure you're curious, how are we going to write this amazing new abstraction? And one port is enough. Though everything will be deterministic except for the one port. Okay? So let's see how we do this. Well, first of all, let's define the abstraction, exactly what it means. Let's specify our abstraction, give the API of the abstraction, and then we will see how to define it. So basically, there's a main thread. There has to be a main thread because it's where we synchronize. So we have a main thread, and all the other threads are subordinate threads. So the main thread will create some threads, and those might create even more, and so on. All those threads are subordinate to the main thread, and then the main thread will wait until all the subordinate threads are done. Okay? So we can define it as follows. We have a procedure called new thread. It runs in the main thread, and it runs this instruction S. S can do anything. And then there is another procedure called subthread that creates the subordinate threads. This is actually an output of new thread. So when we run new thread, we will define also the procedure subthread. And inside S, we can call subthread if we want to create subordinate threads, as many as we want. Okay? And it's also can be done recursively. The S instruction calls subthread, and the argument of subthread can also call subthread. Okay? So subthread can be called inside either of these two instructions S. And then the main thread that calls new thread here, the main one, will wait until all of the subthreads are done, including the subthreads that are created during the computation. Okay, so we don't know how many. It depends on S, the instructions that we execute. We can be creating many, many, many threads, but new thread will wait until they're done. So that's the API of this abstraction. So let me go to the chat. So is that a clear API? Is that API clear? We will define the procedure new thread, and this procedure will create another procedure called subthread, and then we're allowed to execute subthread inside the statement S, and also inside the statement S that's part of subthread. Okay, it can be called recursively as deep as we want. You can see that this is a very powerful abstraction. Okay, and there's no way to do this without a port. Is that clear how this abstraction works? Okay, so now let me go back to the slides and explain how we're going to do it. Let me now show you the magic algorithm that will actually implement this powerful abstraction. Okay, so you understand that this is actually a very, very strong abstraction. It's doing a lot of powerful things. So how can this work? The way to make it work is by using a port, and the algorithm is as follows. So let me show you the algorithm of the abstraction, and you'll see how it works. So here the time runs from left to right. Each of these lines is a thread. We start by calling new thread here. Okay, so what happens? Well, let's say we create another thread here. So we have a second thread here, and it terminates there. But during the execution, maybe it creates a third thread. This third thread maybe runs farther than the second one. Maybe the third one terminates here, but before terminating it, it creates another thread. So you can see threads can create children that live longer than themselves. A thread can create a child thread, and then it terminates. But the child thread can go on, and it can create more children threads. So you can have lots and lots of threads, even though the parents maybe are terminated already. So how do we keep track now? Well, we want to count the number of active threads. So we're going to make a tally, so a count. We're going to count dynamically the number of active threads. So how do we do this? Well, we'll use a port, and each of these threads will send +1 or -1 to the port. So a thread will send +1 to the port when it's created. So then the +1 appears on the stream, and if you keep a count of all the numbers on the stream, this will increment by 1. And when the thread terminates, it sends -1 to the port, so that the count will be reduced by -1. Okay? So the idea is that here, when this thread is created, we will send +1, so the tally is 1. Okay, sorry, the tally is 1. When it creates 1, the tally will be 1 here. We'll create another thread. The tally will be 2 with these 2 threads. This thread will be reduced. The tally will be 1 again. Here we again have a +1. Here we have a -1. So here at this point, the tally is still 1. There's 1 thread. Here again we have a +1, so the tally is going to be 2. Here we have a -1, so the tally is 1. And here a final -1, and the tally is 0. So we keep track of this number, and each time a new +1 or -1 appears on the stream, we increment, we keep counting until it reaches 0, and then we're done. Okay? So we need a way then of keeping the running total of the numbers on the ports. So that's the basic idea. Actually, it's not so simple. It's a bit tricky because you have to be very careful exactly when you send the +1 and the -1 to make sure that you don't have an error in the count. Okay? The idea is to send the +1 just before the thread is created, and the -1 inside the thread just before the termination. So we will see that this works. So how can we be sure that this works? Actually, we need a proof of this, okay? We will reason on this. We will make a proof that this actually works. We have to reason using induction, okay? Otherwise, we could have a bug, and I'll show you how tricky it is. So the send and this plus and -1 has to be done exactly at the right time for this to work. Good. Let me go a second back to the chat. Okay. So is the idea of the algorithm clear? That we will use the port, so all the threads we create will know the port and will be able to do send. This is okay. It's n to 1. And they will send +1 and -1 at different times. And then in the main thread, we will be following the stream and adding plus and -1s until it reaches 0. And when it reaches 0, then the main thread will synchronize. Then the new thread call will terminate. Okay? So you see the idea, how it works. Okay? Well, let me go back now to the slide and explain a little bit more how we're going to program this. So this is the basic idea. So we keep the running total on the stream. But we have to do it in a very precise way to make sure that nothing goes wrong. So here is the basic implementation of it. Okay, so we have the procedure new thread. Subthread here is an output. So here is the procedure subthread that we're going to define. So it's actually an output. So we will create a new port. Notice The argument to new thread is this procedure, is actually the statement S. So the port, I'll call it PT, port. So there's no confusion between the procedure and the port. And the stream is S. Okay? So how does it work? Well, the procedure subthread will send 1 just before creating the thread. Then it creates its subordinate thread. It runs P in there, and when it's done, it will send a -1. Notice the -1 in Oz is actually tilde. Because of the parser, in Oz is because of the generality. Camel also does that. OCaml also does a similar thing. So this is a -1 in Oz. So it will send a +1 before and a -1 inside the thread. So that's the procedure subthread. The main computation will then start. So now we do one call to subthread. This one call will use the original P argument, and it will run in the original thread. So we'll start by doing a send +1. This will start by doing a send of 1 in the original thread here. And it will immediately create a thread, and then it will run ZeroExit. So ZeroExit is a procedure that will read the stream and keep a running sum, and it will exit when the sum is 0. Okay, but otherwise it keeps running until the sum is 0. So this is the definition. Is this definition correct? We will have to argue, make a reason about that. Is this definition correct? Notice there's some subtlety here. The send is done before the thread creation, and the send of -1 is done inside the thread. Is it correct? Who knows? Here's another version. So this is the version that I show you here. Now let's look at this second version, which is a little bit different. What about this version? So here, the send, we do a send of +1, we do P, and then we do a send of -1. But both of the sends are done inside the thread. So what about this definition? Is this one correct? Actually, this one is buggy. Okay? This one is buggy. So this is a bug. How can we know that it's a bug? How can we know that something is wrong? Well, in this definition, it's possible for ZeroExit to stop even though the sum is even though there's still threads. So it's possible for the running total to be 0, but still thread is running. This is possible. So this definition is buggy. How is that possible? Well, assume that we're creating threads. Okay, we create a thread now, and then we send a +1. But before we send the +1, the thread already exists. So that means we've created a thread, but the thread is not, for this short time, the thread is not showing up on the stream. And that means that maybe the stream goes to 0, but this thread should make it +1, but it will only make it +1 after the send. But the send is coming after the creation. So it might be that ZeroExit will exit even though there is still a thread executing. Okay, so this is buggy. So we really need a proof of this. Okay, so what I want to do now is to show you how to prove this. Okay, if you really want to understand, I would suggest you make a scenario, a precise scenario with threads, and show why this version is buggy. You can actually show why it's buggy by doing that. Okay, So we need a proof here. So do you see that? You see this is not so simple, huh? This problem. I showed you two versions. One where the send is happening just before the thread creation, and the other one where the send is inside the thread creation, and the second one is actually buggy. So we have to do some reasoning on this. We have to actually convince ourselves that it's correct. So it doesn't seem to be easy, huh? So let's show how we do this reasoning now. This reasoning actually is going to use an invariant. So we need a proof. Okay, well, we're going to make a proof now, and we're going to make a proof using invariant assertions. Now, we already talked about invariants for loops and so on. You've seen invariants in other courses. I am sure that some of you are not convinced that invariants are really useful in practice. Maybe you've seen them on toy programs and says, yeah, they don't really help. I dare you to show that this program is correct without an invariant. Here we really need the invariant to convince ourselves. And this is a concurrent program. Because of the scheduler, because of the interleaving, things can happen in many different orders, and all of those orders have to be correct. Okay? So I don't see any other way of convincing myself other than reasoning using an invariant. So let's do an invariant. So let me make an invariant here in red. The sum of the elements on S is greater than or equal to the number of created threads. So I'm creating threads. Okay. So actually it should be the number of active created threads. When the thread is terminated, then it will no longer be counted. So the number of active threads. So then the sum of the elements on S is greater than or equal to the number of active threads. So this is an invariant, and we will show that this invariant is always true. We will use induction to show that it's always true. And if this is right, then if the sum is 0, then the number of active threads is less than or equal to the sum. So the number of active threads, it should be active, huh? Active threads will be 0. And that means we're done. Okay? So we will use induction. So the base case, so we will look at execution steps. So it starts, the program starts executing, and it will do steps. In the base case, in the very beginning, it's true because both numbers are 0. Okay? There's nothing on S, and we have not created any threads yet. And then there's the inductive case. Well, what do we have to worry about? Well, in general, we have all possible execution steps we have to worry about. All possible executions. This seems to be very hard, but in fact, it's not that hard because there's only 4 possible steps that could change the truth of the invariant, which I'll show you. Okay? So we'll see that in the next slide. And finally, the invariant assertion is a safety property. That means it's something that is ensuring that the program is not something incorrect. We also need liveness. We also need to make progress. Okay? And this is, we start by sending 1 to S so that we are actually able to continue the execution without stopping immediately. But let me now look at the inductive case. There are 4 possible actions that can change the truth of the invariant. So these are the 4 actions. There's only 4 things, 4 things that can change the truth. Well, sending a +1, clearly. Starting a thread, because we're talking about the number of active threads, sending a -1, and terminating a thread. These are 4 actions that could change the truth value. Now remember, the invariant says the sum of the elements is greater than or equal to the number of active threads. Okay, so the sum on S greater than or equal to number of active threads. That's our invariant. So if we send a +1, well, of course, it can only increase the sum, so it's not a problem. If we start a thread, that means we're actually increasing the number of active threads by 1. Okay, this actually also keeps the assertion is still true, since there is a send of +1 that is following it. Now notice the send, this is the start of a thread, this is a send of +1. Both of these are happening in the original thread. That means this send will happen before the thread creation. Okay, so when we start a thread, it must follow a send of +1. So the send of +1 has given us a margin. So when we do the send of +1, before the send of +1, the invariant is true. We send +1 and we get an extra increment. And so starting the thread will also increment this. So we've incremented S and we've incremented this. So that means the invariant is still true. So you see, it's very important that the send and the thread creation are both done in the original thread. That means that the order of them is known, okay? That the send of +1 must be before. Okay, now let's look at the send of -1. So the send of -1, let me show you the code here. The send of -1 is done here, and then the thread is terminating just after. So the send of -1, actually when we do the send of -1, the thread still runs a little bit before terminating, but it does no work here. Nothing, no other actions are done. Okay, without loss of generality, we can assume that it terminates just before the sending of -1, because when we send -1, there is no work being done until the thread actually terminates. Okay, so that is an empty execution, so it doesn't really matter. So we can assume that the thread termination occurs just before the send of -1 without loss of generality. So that is correct. You see, it's a little bit subtle, but it's clear. And finally, terminating the thread is not a problem, of course. You can see why the send of +1 must be done outside of the new thread, because both the send and the thread creation have to be done in the same order. They're both done in the original thread, okay? Both in the original thread. So the order is known. Okay? So you can see how it works, huh? You can see why that this has to be like this. Okay? And then there's the ZeroExit procedure. This is the final thing, and then we're done. So you can see in the ZeroExit procedure here. So ZeroExit keeps a running sum of elements. So n is an accumulator, actually, here. Keeps a running sum. It takes an element x from the stream. It looks at n plus x. If n plus x is 0, then it's done. No recursive call. Skip. Otherwise, it does a recursive call with n plus x. So notice this always reads at least one element. It will always read at least one element. So that means when we do an initial call, ZeroExit of 0, then it will read one element. So you have to read this one element, which will be +1, and it keeps going until it's 0 after that. So if you look at the code here, you look at the call to ZeroExit here, it starts with 0, But because it always reads at least one element, it will keep going, starting from the +1. Okay, so that's important. So let me now actually execute the beast. Okay, after all this. But first, it's actually almost 9:30. Let me let me execute it now quickly. So I go back to the chat. So you see, you understand how this has to work, how that new thread has to work, and how that the sum is done. So you can understand it's very important, the definition of subthread, and exactly when it does the send of +1 and the send of -1. This is super critical. So let me show you now some code here. Let me write some code. So now let me do dynamic concurrent composition. So new thread. So it takes a procedure argument and it will return a subthread as an output. So subthread is an output procedure. So it will create a port. So there's a stream. The port PT, I will call it PT, as I said before, new port. And I will create now a procedure. Notice I don't have to declare subthread. I'm defining subthread here. So this is actually an output. This binds the output variable, which is the output subthread, because it actually defines the procedure. You see that? And then I can actually create the first procedure. This is this P actually, creating it. And then I call ZeroExit. I still have to define ZeroExit here. So ZeroExit, 0s, done. So the code of subthread is critical here. So subthread is going to do this. The basic idea is this. It's going to do thread. It's going to create P inside a subthread. But now it has to do a send of + and -1. You see, it's extremely important that the send is done outside the new thread. It has to be done outside. That's super important. Okay, and the send of -1 has to be done inside. But that's also very important. It has to be done after this termination. This has to be done inside. So it's using a tilde, which is -1 and as. This must be done inside the new thread. Both of these are very important rules. Okay. And also I need to define the ZeroExit procedure. So ZeroExit NS. So N is an accumulator. I have to always read at least one element. So now I read X here. If N plus X is different from 0, then I do a recursive call. N plus X S2. Okay. Like this. Here the definition is a little bit different from what I showed in the slide. So if N plus X, so the running sum is different from 0, then I do a recursive call. If N plus X is equal to 0, there's no more recursive call, and the ZeroExit terminates. And this ZeroExit is defined before the in, so it actually will define the procedure, will declare the ZeroExit. So it's not like this subthread, which does not declare subthread because it's after the in. This subthread is actually binding this argument. Okay. So this is the definition. So this complicated, very powerful abstraction can be defined like this. Notice this is very dense code. So I'm using higher order here. I'm using dataflow, synchronization, and I'm using ports. in this programmer. So I can show you an example of this. Okay, so let me define now call new thread. But first, new thread will actually create an output. So new thread, and now I can define some statement here. It's actually not a list; it's a single statement. So I can do something like. Let me do something simple. Subthread. Here I also have a procedure. Delay 100. Browse A. End. Like that. Another thread. Okay. Delay 200. Browse B. And then another subthread. I'll do at least one recursive subthread to show you that. Browse C. Okay, like this. Okay, I'm to make sure I'm calling it right here. So new thread has a single procedure argument, which is the statement. So subthread will be bound by the new thread call. So these subthreads will do the right thing. So this one has a procedure that will delay 100 and then browse A. Let me put a simple browse D at the very end here. The second subthread will wait 200, then browse B. And then it will wait 50 milliseconds and browse C. Browse D, and at the very end here, I can browse E. So the idea is that the E will be done at the extreme end of everything, so that new thread will actually wait until all of the subthreads. And you can see you can nest as many as you want, and you can even do if statements to decide whether or not to do subthread. Okay, so let me run this. D, A, B, C, E. If you look here, D, A, B, C, E. Is that correct? I will leave that up to you to figure out whether what this thing should print and whether it's printing right. Okay? So let me go back to the chat now. So here, so is that understandable? Is that reasonable? Notice you should go back. I'm going to record this. I'm recording it now. You should go back and look at it and think very carefully about the proof of this concurrent program, because it's very useful to understand this. It's very powerful, and you could be able to use this in many other programs. So I'm going to do now a small break. I'm going to wait for a few minutes. So what I'm going to do is I'm going to mute my microphone and give you a small break, and then we'll continue.